SwayamPrabha. Digital India. Educated India.
Hello everyone. So, we continue our discussion on the solid propellants, and if you recall, in the last few lectures we have covered various topics under this module. Like we started with the general discussion on solid propellants, then we talked about the propellant ingredients, the basic propellant ingredients, then we talked about the selection criteria for propellants, like what are the major characteristics of propellants which are considered while selecting solid propellants, and in general actually for other propellants as well. So, the general selection criteria for propellants were discussed. We discussed the propellant ingredients in details, like starting from fuels, oxidizer, binder, the curing agent, plasticizer, burn rate modifiers, and so on. There may be like numbers of many propellant ingredients have been tried, but we have talked about the major ingredients. And then we talked about the classification of solid propellants, like in terms of their homogeneity. We have talked about like if the fuel and oxidizers are mixed intimately, then we told that that type of propellants are homogeneous propellants. For example, like double base propellants are the homogeneous propellants, where the major ingredients are nitrocellulose and nitroglycerin. And then we talked about the heterogeneous propellants like composite propellants, where polymeric binder is used to bind the solid fuels and solid oxidizers. For example, like the common composite propellants is ammonium perchlorate as oxidizer, HTPB as binder, and aluminum particles as fuel. Now, if we modify the double base propellant by adding some amount of ammonium perchlorate as oxidizer, or even organic oxidizers such as HMX or RDX, then we can improve some of the properties in terms of like either physical properties and ballistic properties. So, once we modify the double base propellant, it is called composite modified double base propellant. So, we have discussed about that. Then we talked about the nitramine propellants, like it is containing HMX or RDX as oxidizers. We also talked about like for certain tactical missile applications where the smoke trail is a problem. So, there the low smoke or medium smoke or even reduced smoke propellants are required. So, generally the propellant containing aluminum fuel, it creates some white smoke in the trail. So, because it converts to aluminum oxide, which creates this white smoke. There are other ingredients, like example of other ingredients such as burn rate modifiers, certain oxide catalyst, certain metal catalyst may also create some smoke in the exhaust. So, in order to have like low smoke or minimum smoke propellants, we need to make sure that it does not contain any metal particles. On the other hand, it should not produce any kind of chlorinated substance as well. So, ammonium perchlorate as an oxidizer is also kind of going to give some kind of a trail of HCl, and sometime water also can condense in a low temperature air, and that can also give some whitey color in the exhaust. We also talked about the other categories of propellant like gas generator propellants. So, in case of gas generator propellants, the main motive is not to produce thrust, rather the motivation is to provide like moderate temperature gas. So, there are various applications of gas generator propellants, like I can talk about like different type of applications where gas generator propellants are used, like pilot emergency escape. There will be like push missiles from submarine launch tubes or land mobile canisters. There will be different actuators and valves where the gas generator propellants are used. one very common example of gas generated propellants is in the automotive airbags. And then we have talked about the ignited propellants, where the major objective of this propellant is to provide like fast heat release, so that it can provide the hot plume onto the propellant surface, and it will provide the sustainable ignition. And then we ended up the chapter with these discussions. So, today we will look at some of the tutorial problems, just to understand like different solid loading, the fuel rich propellant or oxidizer rich propellants. What we have already learned, one parameter we have learned there is called mixture ratio or MR, which was defined as the mass of oxidizer by mass of fuel. So, applying those understanding, we will try to solve some numerical problems, so that we can very much familiar with what we have covered in this chapter. Okay. So, before moving into the tutorial problems, let us look at one parameter is called like solid loading ratio. Now, if you recall, the very common oxidizer used in composite propellant is the AP or ammonium perchlorate. Now, AP has different particle sizes, and based on the particle size ranges, they are categorized like either it is a coarse particle. So, it may be like varies from 400 to 600 micrometer or micron. So, 1 micron you can know 1 micron is 10 to the power minus 6 meter. Now, another category can be like medium, which is in the range of like 50 to 200 micron. Another category can be fine, which is 5 to 15 micron, and there is ultra fine, which is some micron to 5 micron. Okay. So, it is not always required that only the coarse or only the medium ranges particles are used. Generally, to improve the loading fraction or to improve the packing fraction. Packing fraction means to minimize the volume of the solid particles. Somehow we have to improve the packing of the solid particles within the rocket motor. So, this fraction is the volume of the propellant, or rather I would say like the volume of the solids when packed to its minimum volume. That is a theoretical condition. So, we want it to be like packed within the propellant grain, considering a very minimum volume as much as solid particles are packed together. So, that will take a very small amount of volume within the propellant grain. So, that is the packing fraction. So, we want to improve the packing fractions by compacting as many as solid particles within the propellant grain, or considering the minimum volume for the solid particles. Like solid particle means we are talking about the aluminum as a fuel or boron as fuel, and the ammonium perchlorate as the oxidizers. Now, there are difficulties while we put too much of solid fractions within the propellant grain, because if you look at the uncured propellant, when we put too much of ammonium perchlorate as a crystals, solid oxidizers, we put aluminum particles there. So, processing complexity will increase if we add too much of solid particles within the propellant matrix. So, that part we must need to take care in order to like maintain the proper physical property or the mechanical property of the grain, as well as the ballistic property of the propellant. So, that there is a trade off between that. Accordingly, the solid fraction is chosen. So, if we look at the solid loading ratio, so by definition of solid loading ratio is the mass of solid ingredients divided by the total mass of the propellant. total propellant mass. Now, this is very true for composite propellant, because composite propellant consisting of the ammonium perchlorate as the crystalline oxidizer, aluminum particles as fuel, and the rubbery polymer as the binder. Okay. So, this is essentially the binder, this is the fuel, and this is essentially the crystalline oxidizer. So, once we say the solid loading ratio, that means we are talking about the mass of ammonium perchlorate plus mass of aluminum divided by the total propellant mass. So, if we are asked to find out what is the solid loading ratio, we must need to add up the mass of ammonium perchlorate and mass of aluminum particles and then divide by the total propellant mass. Okay. So, it is the mass of solid ingredients divided by total propellant mass is the solid loading ratio. So, I will try to see through some example problems like how we calculate the solid loading ratio and how that are going to influence the the ratio of oxidizer to fuel, whether it is becoming oxidizer rich or whether it is becoming fuel rich. So, we will look at those things through one example problem. Now, solid loading can be as high as 90%, because to improve the performance, we may want like solid loading as high as 90% in some composite propellant. But of course, the high solid loadings as desired for high performance, but that will introduce some additional complexities as well as the cost enhancement or cost increase. So, there must be a trade off between the ballistic performance and the physical properties, the processability, the manufacturing capability, all those things should be taken care of while choosing the solid loading ratio. Okay. So, with that I think it is pretty much okay with our theoretical stuff. So, now let us look at some typical tutorial problems where we will try to brush up some of the basic stuff what we have just learned in these few lectures. So, let us look at one tutorial problem. If you look at the problem statement, it says a composite solid propellant consists of the following ingredients. So, it has like AP as oxidizer, HTPB as binder. So, it is typical composite propellant. We already know that typical composite propellant contains AP as oxidizer and hydroxyl terminated polybutadiene as binder. Now, they are mixed in stoichiometric proportion. Let us assume the molecular weight of HTPB is 2734 kilojoule per kilomole. Now, it is asking us to find out the mixture ratio and the solid loading in the problem. Okay. Solid loading in the propellant. So, it is asking about how much solid loading ratio is there. So, this is an example problem taken from one book by Professor Ramamurthy. So, we just look at how we understand the theory part. So, we will just simply proceed with that. So, as it is given to us the stoichiometric proportion of the AP and HTPB. So, they are mixed in stoichiometric proportion. It is given in the problem statement. Okay. So, it is basically solid loading in the propellant, that will be the correct I think word. Okay. What about the chemical formula of HTPB? We have earlier learned this, that it is like a hydroxyl terminated polybutadiene. So, it will have like butadiene, many butadiene chain structure connected together. So, it will be like this N, and it will have hydroxyl radical at the end. So, this is the typical formula of HTPB. Now, we can write this in a little simplified form. We can write this as C4H6N OH2. There are hydroxyl radicals at both the ends. Now, since the molecular weight is given as 2734 kg per kilomole, let us try to write from there what we can write from there, that how many, we can get like how many carbon, how many hydrogens, how many oxygens are present there, and accordingly we can find out the number n. So, let us try to do that. We can write 4 carbon. So, it is like 4 into 12 plus 6 into 1. So, that is 6, that is times n, plus we have like 6 plus 1 into 2, that is going to be equal to 2734. So, if you solve it, I think we will get, solving this one, we will get n equal to 50. So, that will essentially give us the chemical formula of HTPB if we put this in this equation. So, this will become, sorry, so this will become, we have like C4H6 into N OH2. So, we can multiply that one. So, the chemical formula will become, based on this molecular weight, we can get C200, H we can put it inside. So, H we have like 2 here and 6 times 50. So, that will become like 302. So, we can have H 302 and O2. So, this is the chemical formula of HTPB we get after solving. Now, since the chemical reactions between the HTPB and AP is given as stoichiometric combustion, since it is given as the stoichiometric combustion of AP and HTPB, what you can write, that all carbon atoms will become like carbon dioxide, all hydrogen atoms will become combined with oxygen will become water. So, what you can write is, and of course, whatever the nitrogen will present will be there, nitrogen present in the AP molecule. So, if you write down the formula for HTPB here, so it is basically C200 H302 O2 plus AP you already know, AP is NH4 ClO4. Now, let us, we do not know how many molecules are going to be reacted with HTPB to have the complete combustion reaction. So, let us write that as A, and we can just simply write CO2 plus HCl is going to form HCl plus water plus nitrogen. Okay. So, we can easily write nitrogen molecule. So, this will become A by 2, easily write, because here it is A N. So, we can write A by 2, and let us say carbon dioxide we know, because there is only carbon atom here. So, we can directly write 200 in CO2. HCl we do not know. So, we can write HA. Okay. We have H here, the other can be like, let us write this as B, H2O. Okay. So, from the balance of balancing this reaction, after balancing we need to solve for it. Okay. If we solve it, I think we will end up getting 2B equal to 302 plus 2A. So, B equal to like 4A minus 398. If you solve for it, I mean, this is not a very difficult task for you people. So, you may easily do it, and you can find out the value of A as 219.6 and B as 480.4. You can check these answers. Okay. You can do yourself and check this answer that you are getting this. Now, you can immediately write the stoichiometric equation after getting the value of A and B. So, we can write the stoichiometric equation, and the stoichiometric equation will become C200 H302 O2 plus 219.6 NH4 ClO4 that will become 200 CO2 plus 219.6 HCl plus 80.4 H2O plus 109.2 N2. So, this is the complete combustion equation or the stoichiometric equation. So, we are asked to find out the mixture ratio. As per the definition of mixture ratio, we have already learned that mixture ratio is the mass of oxidizer divided by the mass of fuel. Now, in this case, since there is no aluminum particles are present as fuel, here the binder is acting as a fuel. So, we have the mass of HTPB and mass of AP. So, we can simply write what is the mass of oxidizer here. Mass of oxidizer is this one. So, we can simply get the 219.6 into the molecular weight of NH4ClO4. So, we can write for N it is 14, 4 into 1, that is for hydrogen, for chlorine it is 35.5, for oxygen it is 16 into 4, okay, divided by, we have fuel here. So, 200 into 12 for carbon, 302 into 1 for hydrogen plus 2 into 16. Okay. If you solve this, you will get 9.44. So, that is essentially the mixture ratio. Now, the second question, so this is the answer for question number A. Now, in the second part of the problem, we are asked to find out the solid loading. So, what is the solid loading or the solid loading ratio? You see, the solid loading in the propellant is the fractional mass of solids present in the propellant. Since this is not an aluminized propellant, there is no aluminum particles present. So, in our case, the solid loading will be simply the mass of oxidizer divided by the mass of propellant as per our definition. So, here mass of oxidizer means mass of AP plus mass of HTPB. Now, if you divide this mass of AP by mass of HTPB, we can have mass of AP divided by mass of HTPB in the numerator, and in the denominator we can write mass of AP by mass of HTPB plus 1. So, what is mass of AP by mass of HTPB? It is nothing but the mass of oxidizer by mass of fuel, which is mixture ratio MR divided by MR plus 1. Okay. So, if you just put the value there, you will get MR we have just found out 9.44. So, it is 9.44 divided by 9.44 plus 1. One can actually calculate this, it will come something around 0.9 or 90% or 90%. So, you can see it is very high solid loading in the propellant. Now, considering the percentage of binder, so here it is like 90% AP and 10% binder or 10% polymeric fuel. This is the combination now what we found out just. So, because this is a high mixture ratio, the mixture ratio is, you see, it is 9.44, and from there we can find out the solid loading is like 90% is solid loading. So, it is kind of difficult to such a large value of solid loading, because in order to bind them, the requirement of polymer will be slightly higher. So, it is very difficult to bind these oxidizer with a such a huge percentage. So, this is one such problem you can solve, you can do the similar type of problems. This will help you to understand the theory part of this portion better. In fact, this will help you to solve some assignments as well. Okay. Now, let us look at the other type of propellants where you can actually find out if the solid loading ratio is given to us, and instead of just only like HTPB plus AP as oxidizer, let us add aluminum particles also, because aluminum particles act as fuel in the composite propellant. So, we can take the example of a solid composite propellant where aluminum particle will be there as a fuel, HTPB will be there as a binder, and ammonium perchlorate will be present as oxidizer. And from there we will try to see that whether it is becoming fuel rich or oxidizer rich, we will try to calculate and understand. Okay. So, let us look at the second problem. So, look at the problem statement first. It is saying a composite solid propellant has a solid loading of 90% and it contains 10% aluminum. The fuel binder is HTPB and the oxidizer is AP. So, fuel or binder we are saying that HTPB, because HTPB will act as fuel as well, because it is hydrocarbon fuel. But here it has proper fuel as aluminum and binder is HTPB and oxidizer is AP. Now, it is asking the question that what is the mixture ratio and molar composition of the propellant, and also it is asking us to find out the composition, whether it is a fuel rich or oxidizer rich. Okay. This problem also taken from the same book, but we will try to understand the we just brush up our understanding what we have learned in the theory course, because this will help us to do the assignments as well. So, let us look at the problem statement and write what is given. So, what we can write from here, as per the problem statement, solid loading is given. So, solid loading is given as 90%. So, we can immediately write that solid loading as per our understanding, it is the mass of ammonium perchlorate plus mass of aluminum divided by the total mass of the propellant, which is mass of AP plus mass of aluminum plus mass of HTPB, that is given as 90%, which is 0.90. Okay. And also it is given, if you look at here, it is given like 10% aluminum. So, we can write that mass of aluminum divided by mass of AP plus mass of aluminum plus mass of HTPB, this is given as 10%, which is 0.1. So, this is equation 1, let us say, this is equation 2. Okay. So, combining this, we can easily find out that mass of AP plus mass of aluminum divided by mass of aluminum will simply become 9, because we are dividing equation 1 by equation 2. So, we can get this, or from here we can easily get like mass of AP plus mass of AP by mass of aluminum plus 1 is equal to 9, or from here we can get mass of ammonium perchlorate by mass of aluminum will be 8. Okay. So, this is another finding. So, from here what we can say that the oxidizer to aluminum mass ratio is 8. So, from there we can actually get the ratio of binder to the aluminum particles. We can see how much is present in the propellant. So, let us say if we want to find out like mass of aluminum plus, we can get from the equation 1. So, from equation 1 we can easily write. So, or even equation 2 also same thing. So, let us say we write from the equation 2, because we are writing mass of aluminum. So, mass of aluminum and mass of AP plus mass of aluminum will simply become 9 times mass of aluminum, because 8 times is the mass of ammonium perchlorate with respect to mass of aluminum. So, we are just writing in terms of mass of aluminum plus mass of HTPB, which is given as 0.1 from equation 1. If you now do this thing, you will end up getting mass of HTPB by mass of aluminum will be equal to 1. So, what does that mean? There is an equal proportion of the polymeric binder and the metallic fuel. So, it is like 10% aluminum and 10% HTPB. So, typical if you write down the mass ratio, it will become like mass of AP is to mass of aluminum is to mass of HTPB will simply become 8 is to 1 is to 1. Okay. So, it is like 80% ammonium perchlorate, 10% aluminum and 10% HTPB. So, now if you try to find out the mixture ratio, what will be the mixture ratio? Mixture ratio will be simply the mass of oxidizer divided by mass of fuel. Remember, this time the mass of fuel will be the mass of binder plus mass of aluminum particles. So, it will be like 8 by 1 plus 1, which is like 4. So, this is the answer for question number A. Now, molar composition, I think one can easily do it. If you try to find out the molar composition can be found out by you just try to do it like number of mole for AP is to number of mole for aluminum particles is to number of mole for HTPB. Since we know the mass, we can simply write like mass of AP by molecular weight of AP is to mass of mass of aluminum is to molecular weight of aluminum is to mass of HTPB by molecular weight of HTPB. Okay. So, if you write down this mass, you already know that was like we can do it, the mass of this one was 8 by molecular weight of, one can find out the molecular weight of this NH4ClO4. So, if you do this, I think you will get 117.5 kg per kilomole. So, you just put the values there. I am not solving fully, I am just writing how to do it. So, you can just simply write, and mass of molecular weight of aluminum is 27, molecular weight of HTPB we can take from the previous example problem, but it must be given there, otherwise it is difficult to say because molecular weight of HTPB varies. So, you can easily find out the ratio from this, and from there you can actually find out the combination of the the molar composition. You can actually get the molar composition . So, it is coming something around 0.672 is to 0.325 is to 0.003. I mean, the participants are requested to verify the calculations once. Okay. So, eventually if you write down the equation, the molar composition of the propellant, you can get like it is containing 0.003 of HTPB. So, HTPB was, the formula was C200 H302 O2 plus 0.672 of NH4ClO4 plus 0.325 aluminum. Okay. Now, in the second question, if you remember, it was asking us to find out whether the composition is fuel rich or oxidizer rich. Now, how do you find out that thing, that whether it is a oxidizer rich or fuel rich? We can actually find out that how many number of hydrogen is present there, because you see the complete oxidation product or the complete combustion products will contain, if you consider like stoichiometric reaction, the complete combustion products will have HCl, then we have H2O, you have CO2, and for aluminum you will have aluminum oxide. Okay. So, we have how many number of hydrogen? So, we can add up like 302 into 0.003. So, it is like for hydrogen if you calculate, it is like 0.003 into 302 plus here we have 4 into 0.672, that will give us like 3.594 hydrogen atoms. Now, out of this 0.672 will be oxidized to form HCl, because you remember there is 0.672 chlorine atom is there. So, 0.672 hydrogen will actually become like HCl, it is going to form like HCl. The remaining hydrogen, so it is like remaining hydrogen atoms is like 3.594 minus 0.672, that is going to take oxygen and will become water. So, like 2.922 hydrogen atoms will oxidize and let us go back. So, it is 2.922. So, how much oxygen atom requires to oxidize hydrogen? To H2O. So, it will be simply like 2.922 divided by 2. So, that much of oxygen atoms required for converting hydrogen atoms to water. So, this will become like 1.461. Now, what about the carbon atoms? So, the carbon atoms will have like 200 into 0.003. So, carbon atom is like 200 into 0.003. So, we can have 0.6. So, the oxygen atoms required for converting C to CO2 will be like 0.6 by 2, 0.6 into 2, because CO2 requires like 2 oxygen atoms. So, it is like 0.6 into 2, which is 1.2. Okay. Similarly, for oxidizing the aluminum, we have like 0.325 aluminum, which will convert to Al2O3. So, the oxygen atoms required for this purpose will be like oxygen atoms required will be like 0.325 into 3 by 2, because Al2O3. So, it is 3 by 2. So, that will become like 0.4875. So, the total moles of O2 required will be this, like 1.461 plus 1.2 plus 0.4875 divided by 2, that will becoming 1.745. Now, you see the number of moles available in the reactants, number of moles of O2 available in the reactants, because that will determine whether it is a fuel rich or oxidizer rich. You can get what is the availability of oxygen molecule. It was like 0.003 plus 2 into 0.672, which is coming as about 1.347. So, this is the available and the required is this one. So, what you can see, it is fuel rich, is not it, because the availability is actually less than the required for the stoichiometry reactions. So, it is fuel rich. Okay. So, similar way one can actually try to find out the ratios, and one can actually understand that whether it is a fuel rich and oxidizer rich like this, based on the composition of the reactants. One can actually do the solid loadings ratios just by calculating the amount of solid mass present in the propellant and divided by the total mass of the propellant. And similarly, if the solid ratio is given, one can actually find out the composition as well. So, these tutorial problems actually help to solve some of the assignment problems later on given to you. Okay. So, I think with that we close this module on solid propellants. Next week, the next class will continue with a new topic. Okay. Till then you can revise this stuff. Okay. Thank you.